Our first speaker of the afternoon is Otis Chodosh from Stanford, and he's going to tell us about his recent work on generic regularity of area minimizing surfaces in 9 and 10 dimensions.
This is working? We're okay? All right. Thanks very much to Rick for the introduction. And it's really exciting to see so many people I know and many people I don't in such a conference again. And so I should also apologize because I don't know how well I'm going to do with these markers. So I may, if anything is illegible, just shout at me, please. And I may also do something which I really hate and not always write all the names that need to be written. I'll say them, but not write. I think you should always write the names when you talk about something, but I may break my rule here. So I'm sorry, especially if I don't write your name. So the basic problem, which I'm going to be interested in here today, so starts if you take like a codimension 2 closed submanifold of Euclidean space. So it should be smooth, embedded, and oriented. Okay, and so I'm always going to be working in the oriented setting today. So if you know what that means, you can fill in the details. Otherwise, just think that everything has some orientation. Okay, and then I'll look at all n manifolds, right, which fill in gamma. Okay. So the right picture to have in mind is in R3, you take a circle and you look at all 2-dimensional manifolds which fill in the circle in this way. And when I write this, I mean this as a sense of oriented boundaries. Okay, so again, M is oriented here, right? So that will be very important. Okay. And the question is, so can you minimize the surface area or whatever, surface area among this class, okay? So can you find an M filling in gamma who has least surface area among all possible competitors, okay? So this is known as the plateau problem. Okay, and so I'll just say that I'm only ever going to work in codimension 1. So that means that the dimension of n versus n plus 1 is 1. So if you talk about higher codimension, basically the story should be very, very different. Okay, so this is very specific to this situation. Okay. All right, and I think there's a very well, from one point of view, there's a perfectly well understood answer to this question. And I think this is one of the highlights of geometric measure theory, geometric analysis. Okay, so the answer is yes, but it can have some singularities. Okay, and okay, and so it can have singularities, but the dimension of the singular set should be quite small. And hopefully I got the numerology here right. I always mess this up. Okay, and so let me just tell you a simpler way of thinking about this. So when the ambient dimension is below 7, so in R7, R6, etc., you get a completely smooth minimizer. Okay. When n plus 1 is 8, actually you get a little bit better than a 0-dimensional singular set. You get isolated singularities. Okay. Oh, and sorry. And 9 and beyond, you get some potentially more complicated singularities. So in dimension 9, you imagine you have a 1-dimensional singular set. Although it may not exactly be 1-dimensional. It might be like a subset of a 1-dimensional set and very fractaling. So Leon Simon recently constructed some examples. It's not clear if they're minimizing, but some examples along these lines. So it's not you don't expect necessarily the singular set is a nice submanifold. Okay, and I should say I think this theorem is due to Federer, Fleming, DeGiorgi, Almgren, Jim Simons, and Hart-Simon. And so I haven't written here, but actually near the boundary, it's completely smooth. So, right, so there's an extra little piece that I'm not going to mention, but it's very important in the whole story. So, all right. Is that clear? Okay, so I should give you the canonical example, which probably everyone could predict what I'm going to say. Okay, and so in R8, there's sorry about that. In R8, there's a sort of a classic example, first proposed by Jim Simons and then proved to be minimizing by Bombieri, DeGiorgi, and Giusti. And so that's this cone. So what this is X in right. So you just take these points in R8, you split it into two R4s, and you look at the points which have equal norm. Okay? And so this is some cone C. And if you intersect with the unit ball, you get a codimension 2 submanifold. You can convince yourself this is like a S3 cross S3, scaled appropriately. And then this piece, so C intersect B1, has the least area among any competitor. And so in particular, any smooth surface which has this boundary has strictly more area than this piece. Right? So there's no minimum among smooth surfaces, but among singular surfaces, because the origin is singular, right? Then you have a singularity in this problem. It's unavoidable. Okay? Okay. So what I'd like to tell you is a way out of this a little bit in certain dimensions. But let me write the theorem. Let's put it here. Okay, and so the theorem, so Hart and Simon proved this in 8 dimensions in the 80s, mid-80s, and then we've added the numbers 9 and 10 to this statement. So if you take a gamma, just like this in this picture, and then you wiggle it a little bit, so you can wiggle. Okay, and so let me not relabel it. So I can perturb it in some C infinity set. So I take like a C infinity section of the normal bundle and I push in that direction. I can do it as small as I like. So that when I do this, then the plateau problem only legitimately has a smooth solution. Right? So there does exist a smooth manifold minimizing area among all smooth competitors, or even singular competitors, but that's not relevant. Okay? All right? And so it's also the unique solution even among singular competitors. That's less interesting. I'm not going to talk about that. Okay. And so I don't know if this is legible, but it's less important. Okay, so you can also do the same thing when you're minimizing in codimension 1 homology. And so this was done by Smale in 8 dimensions. We can also do 9 and 10 dimensions. Okay, so I think the experts can fill in the details, and if you don't know, then it's not that interesting. Okay, so I should give you an example of why you might, why do you believe that these singularities maybe could be perturbed, right? What's the, why is there any hope here? And so we only know one example of a singular minimizer anyways, and so I'll just say, what I'd like to say is that Bombieri, DeGiorgi, and Yusi proved that this cone minimizes area. And they did this actually by constructing some other area minimizers, which are smooth. So what they did is they used ODE methods to find the blue surface. Okay, and so this surface is completely smooth. And it lies on one side of the cone. And it's also an area minimizer. Okay, and so when I say area minimizer for a non-compact surface, that just means any compact piece that has a boundary gamma, then that part minimizes area. Okay, and so the existence of these actually proves the cone is area minimizing, but I won't say why, it's not hard. But what this does for the purposes of this talk is, here's my perturbation, right? So if I have gamma, the minimizer is singular, well, I should jump to gamma prime and find a smooth minimizer suddenly, okay, right? So just in the simplest case, you see that this result is true, right? And it's known it's known not earlier than what I'm talking about. Okay. So the first question you have to ask is sort of what kind of perturbations should you be looking for, right? So how do you hope to perturb? And so if you think about it if you take gamma and apply a translation, that's kind of bad news because the minimizer will just translate and you haven't gained anything, okay? So you're going to need to choose some special kind of perturbation. And the idea really goes back to Hart and Simon. So you should take one-sided. Okay, so in the setting at hand, it's a little bit mysterious what that means, but I'll just draw the picture and you're going to have to trust me that it really makes sense. Okay, so suppose we have some boundary gamma and an M, which is a minimizer, but maybe it's singular. Okay. And we'd like to perturb gamma. And in this picture, it's kind of clear what it means to go to one side. We want to perturb to here, right? In this direction. Okay, it's a little confusing because what does one-sided mean? But you can make sense of this pretty easily. All right. And so what I want to arrange, so I can do all of this while arranging that the minimizer for gamma prime lies very close to M. So in particular, when I converge back, I'd like to say that M prime is converging from above to M. That's always going to be the situation in hand, okay? All right, so with a little bit of work, this is doable. And so the idea that really goes back to Hart and Simon is that M prime improves. Right? Somehow, relative to M, M prime is going to be better, as long as you get close enough. Okay? All right, so in order to explain our contribution, I think I need to explain more or less what Hart and Simon do, so that's what I will do now. Okay, so let's restrict ourselves to 8 dimensions, and this is the Hart-Simon situation. And what Hart-Simon prove is actually better than improves, but Hart-Simon claimed that M prime is completely smooth. Right, so you found the smooth, the perturbation so that the minimizer is completely smooth that you were looking for in the beginning. Okay? And so, of course, when I say M prime is completely smooth, I mean that for gamma prime sufficiently close. Right? So, in other words, for contradiction, I'll assume okay, so I'll assume that M prime still has some singularity, even as no matter how close I get. Okay, so let me modify my picture. All right, so here's my picture. And so M prime is supposed to be having a singularity here. Let's call this X prime. Okay. And then, so in the limit as M prime goes to M, X prime limits to some point X. Okay. And so in this sort of business, whenever you have epsilon regularity, a monotonicity formula, I'll talk a little bit more about this later, but in general, you can expect that singular goes to singular. Right, so in particular, you know that because X prime is limiting to X, X is actually going to be a singular point. Okay? And so what I can do, now I can look centered at X, and I can look at X prime and rescale so that the new point is a distance 1 away. Okay? So I'm going to take a blow up and get some contradiction. Okay? And so when I do this, because I'm sitting at a fixed point, this is a little bit like Richard was talking about the self-shrinkers. When you sit at a fixed point, you expect to get something self-similar. So M should limit to some tangent cone. Okay, so blow up of M. You get some tangent cone. And the blow up of M prime, well, here you just get some limit. Right? So it shouldn't necessarily have any self-similarity because you're taking around some, like you're not centering around a fixed point and zooming in, you're letting the sequence of flows change, and you're changing the scale. So you get some M twiddle and some X twiddle, and this is supposed to be the limit of blow up, like the blow up of M prime. Okay? And here now I've arranged that this distance is 1. Okay? So, but I've drawn my picture wrong, I guess, because I told you that singular points limit to singular points, right? And so you in particular, you know that X tilde has to be singular. Okay? And so what I didn't say exactly is that M prime should lie weakly on one side of this cone, right? Because that was, I haven't really told you what one-sided means, but I've worked sort of so that M prime locally is above M. So maybe I converge to the cone, but in 8 dimensions, that's not happening because the cone has to be completely smooth. That's a part of the regularity theory, okay? So in particular, I found some M twiddle lying to one side of the cone, which has a singular point. And this is some complete area minimizing surface, maybe with singularities. Well, with singularities in this case. Is that okay? Okay, so I probably shouldn't have erased this picture. I'm regretting this now, but that's life. So this is going to contradict the following theorem. Okay. Okay, so consider an area minimizing cone in hypercone, and assume that its singular set is precisely the origin, right? So it's not the flat space, but also doesn't have more singularities away from the origin. So the link is smooth. Okay, right? Then so take the complement of the cone. That's two open sets. And then there exists in each of these open sets some hypersurfaces, which are area minimizing. Right, so these are non-compact, so all the compact pieces are area minimizing. And the homotheties of them foliate the entire complement. So each side is foliated by these, they're star-shaped hypersurfaces. All right? And so this is where I'm regretting my picture being erased, but I'll draw that really quick. So this was the Simons cone, and here's the Bombieri to Georgi-Giusti hypersurface. Well, then if you take dilations, you actually foliate one side. And here everything's symmetric, so you can just flip over onto the other side. Okay? In general, the S plus and S minus may not look exactly the same. And oh, sorry. And so I should say these are smooth. And I want to call this point I. And point I is also important, which is that any M tilde, let's say lying in U plus, but of course the same thing for U minus, right? Right? Area minimizing complete. By complete, I don't mean no singularities, I just mean no boundary in the sense of currents, okay? If you have any area minimizer lying on one side, then M tilde is lambda S plus for some. Okay, right? So not only is there this foliation, but any a priori minimizer lying on this side, actually this picture doesn't exist, and it has to be one of the leaves. Okay? All right, and so let me first, there's been some work that I should mention about this result in a second, but let me just first say why this finishes the Hart-Simon result. And so, well, remember, because M prime was assumed to be singular here, I blew up. I got a singular surface on one side, right? But it's an area minimizer lying on one side of a cone. I said 8 dimensions, the cone is smooth automatically. But therefore, it must be a homothety applied to S plus or minus, but S plus was smooth, okay? And so that's a contradiction. Okay, and so, so actually, there's been recently some exciting progress on this theorem when the cone is not, doesn't have this property. And all of the authors are here, so I'll mention. Right, so I is all cones, and this is by Zihan Wang. Right, so you can have, there's many area minimizing cones which are not, don't have this property, and I'll talk some about that later. And so the existence of a smooth area minimizer on each side, which foliates, is done by Zihan, and then okay, and Nick and Gabor recently showed that the uniqueness statement holds when the cone is replaced by, instead of a smooth cone, it's a cone where the singular set is some whole RK, right? So like, it's easiest to imagine R across a cone. They have there are some restrictions on the cone, but I won't talk about that. I guess Gabor might mention that result, okay? Okay, so in particular though, I will say that 2 is definitely not known at this moment for all cones, right? That's very open. Okay. Are there any questions now? Yeah. Excuse me? For gamma. Yeah, so you don't need any sort of, you just need to be embedded hypersurface. But it's better to assume, just in your mind, just think of it as connected. But certainly you don't need to do that. In our theorem, no. In Harden-Simon, it's a little bit, Harden-Simon don't state this precise theorem. So if you look in Harden-Simon, I think they morally proved this, but they don't quite say exactly this statement. So we're very careful to prove this theorem under the possibility where there's a disconnected gamma. There's some interesting GMT features of that problem. But it's true with disconnected. I don't want to put words in Harden-Simon, it's a little bit unclear. Like they reduce to the case of oriented boundaries very quickly. And that reduction is a bit hairy in the disconnected gamma situation. Yeah. Thanks. That's a good question. Any other questions? Okay. Okay, so in the rest of the talk, I'd like to kind of explain the difficulties of generalizing this to higher dimensions. Okay, so in my view, there's two main problems with proving this theorem in R9 that don't happen in R8. Okay, so the first problem is the II in the HS theorem isn't okay. So the first issue is that the second uniqueness point is unknown for general cones. Right? So if you have a singular cone, unless it's of this special type considered by Nick and Gabor, we don't know that the one-sided surfaces are unique. Okay? So uniqueness is less important, but if you could prove smoothness, that would be enough. Maybe there's non-unique, but they're all smooth. That would work for this blow-up argument. But at the moment, that seems like a pretty difficult problem. I mean, their result is already quite non-trivial, and to do it in general, I think is out of reach at the moment. Okay. But worse yet, in some sense, the blow-up argument doesn't work. Okay, so this picture, where you zoom in, you rescale, you get this thing lying on one side, this completely breaks down. Okay, and I'll explain that in a minute. Okay, and so I'm going to decouple these issues. So I'm going to first explain how to resolve this issue, and then I'm going to forget my resolution here and pretend that this issue you could prove Hart-Simon for all cones and explain this issue. All right. So in reality, you have to do something a little bit more, but it's not so serious. So okay. Where did my eraser? Okay, so what I'd like to talk about now is, I'll start here. And so what do we do? So we don't prove the Hart-Simon theorem for general cones. That's too hard for me, certainly. I hope someone will prove it. But instead, actually, we discovered, and we already had discovered this in an earlier joint work also with Kyung-Soo Choi, that you can get away with doing something much weaker than the Hart-Simon theorem. So you can kind of wheedle your way out of the needing to prove this difficult, right? This is like a very analytically and geometrically difficult theorem, because at the end of the day, you're really saying some solution to a nonlinear variational problem equals some others. Like this is very difficult. Okay? But what we prove actually is quite simple. And this is with also Choi. And in the paper I'm talking about now, you have to modify this proof a little bit, but OK. So I'm going to tell you the weakening of this theorem for a cone with an isolated singularity. But if you're an expert, in 5 minutes, you can write down the general. If you know about cone splitting, you'll write down the general statement. Okay. So. Okay, so suppose you have a cone with only the origin is singular. And suppose you have this m tilde minimizing in, say, u plus to one side of the cone. OK, so I need to pause and define for you the density. OK, so probably many people are familiar, but let me just come over here. Okay, so if you have an area minimizing surface, and you look at the volume of or the area of the surface in the ball of radius r, and divide by the volume of the n ball of the radius r, right, then this quantity is increasing as you increase r. Okay, you shouldn't hit the boundary when you do this, right? You want to work with smaller balls than are hitting the boundary, right? And so in particular, so the limit as r goes to 0, this theta m of x, this quantity always exists. So you have a monotone function. You can take the limit. Okay? And so if you have a singular cone, or more generally a singular point, then you always have density bigger than 1. Right? This is an epsilon regularity type theorem. So DeGiorgi and Allard prove this. And then density the density is always 1 at a smooth point. Okay. All right. Okay. Is that all right? So hope that's like a crash course in monotonicity. But in particular, let me just notice that the last two things I wrote. So if you know Hart-Simon, right, then m tilde has to be smooth. So therefore, this number is 1, and this number is bigger than 1 plus epsilon. So this theorem is much weaker than Hart-Simon, right? So this is like a bad version of Hart-Simon. But this is actually enough to prove the theorem, to the Hart-Simon theorem. Okay? And also the proof is easy enough that I can show you now, more or less. Okay? And then, so in 8 dimensions, actually, you can improve this by compactness, right? Whenever they set the space of minimizing cones with smooth cross-section is compact in 8 dimensions, but not necessarily in higher dimensions. When you have some inequality, you can always squeeze a bit, and you have a compact set, you can always squeeze a bit out, right? So in 8 dimensions, you can put a minus eta here. And so I'll let the experts think a bit about how this statement is appropriately written in higher dimensions, but I'm not going to do that. So I think I'm going to go out of order here. And so let me show you why you should believe that this statement, which is much weaker than the Hart-Simon statement, why this implies the 8-dimensional regularity. Okay? And so let me relabel things a little bit. So it's useful now, instead of having one sort of perturbation, I want to consider sort of the whole continua of perturbations. And I want to define this quantity d of s, which is going to be the max over, ms. So instead of m prime, right? So in reality, there may be non-unique minimizers, but I'm going to pretend that there's unique minimizers, okay? So you take the maximum over all points, M and S, of the density, okay? And so this quantity is somehow a measure of the sort of the singularity of this MS, right? So bigger density should be sort of more singular, I don't know. So if you can push the density all the way to 1 by the epsilon regularity theorem, then you've found a smooth solution, okay? So the goal is to say that, well, that ds is 1, something like this, right? So what I should do here is I claim is that lim sup of ds as s is going to 0 versus d of 0, actually I drop by eta, where that's that eta, okay? And now, okay, there's nothing special about 0. Now it's like a exercise in real analysis to say that if you always have this property, you can perturb finitely many times to go below 1, okay? Right, so, okay. I should put the singular set, and then I get minus infinity, but that's just a technical issue, okay? Right? And so, well, the claim is very easy. So I take xs achieving this maximum, right? Then I do exactly this blow up procedure, right? So then, let me just write down the inequality. So okay, sorry, let me just see. I always get confused here, but so the cone has density at most d of 0, because this was the measure of the biggest density of any possible singularity, right? And then this assumption, if this failed, I would get that the density of m tilde at x tilde, which is my blow up point, should be bigger than d of 0 minus eta. Let's see if I got that right. No, sorry, it should be bigger than equal, sorry. Right, so if this was false, then I could find si limiting to 0 and take xsi for that choice, so that the limit of this quantity was bigger than or equal to this, right? And then, but now here, this is bigger than equal to theta c minus eta, right? And that contradicts my theorem. I think I somehow jumbled that a little bit. Okay, so if you blow up this statement in this problem, you get this strict drop. And so the interesting thing is here, so in Hart-Simon you perturb sort of once, and in this statement you perturb once, then the d goes down a little bit, you perturb again, it goes down more, but eta is sort of fixed for this whole situation. So let me quickly tell you how you prove this proposition, because the interesting thing, I think, is that this proposition is very easy, and it should suggest to you that we could also make it work for singular cones. Might try the other black. Oh, is this another one? Oh. Oh yeah, here we go. Okay, so here's my proposition. If I have my cone and my m tilde on one side, then the density at any point is supposed to be strictly less than the density of the cone. I'm not going to prove the eta. That's a compactness argument. Okay? So assume for contradiction that that's not true. Okay? So the first step is to take the blowdown of the blowdown of this cone, right? So you look at the tangent cone at infinity, right? So what you should say that the tangent cone at infinity to m tilde is c. Okay, so I'll just say in words why that should be true. So you get the tangent cone at infinity to m tilde should lie on one side of c weakly, right? But it also sort of, it has the origin in common. So the strong maximum principle already is telling you, you can't have two cones, like two distinct cones lying like this. Okay. So then what this says, well, monadicity tells me that the density of m tilde at x tilde is smaller than any finite radius. But now let this radius go to infinity, and then I measure the density of the tangent cone at infinity, which is theta c. Okay, right? So now, if I look at my steps, well, this is bigger than or equal to theta c, so actually it should be equal, and here I have equality for every step. Okay, so this tells me, I didn't say it, but if you have in monotonicity, if you have equality in the monotonicity formula, you actually get that you're a cone on the nose. So m tilde is a cone centered at x tilde, but the tangent cone to infinity is c, so it's actually c shifted by x tilde. Okay. And now I won't prove this, but it's a geometric fact that x tilde had to be 0, right? So for a non-trivial area minimizing cone, you can't shift the cone around and remain disjoint. Of course, for like the cone you have in your head, it looks like this. You go up, but that cone is definitely not minimizing area, or it's not even a minimal surface. Okay, so I'll leave this as an exercise where you can think about it. Okay, and so this is a contradiction because we assumed we laid on one side. Okay. Are there questions about that? And so, okay, and this argument is quite robust, even if you have a singular set. You'll end up proving that if you lie weakly on one side, then you can only have less. You're less than like strictly equal to unless you're equal to the cone and you lie in the spine of the cone. Okay, so this is nice, and so this lets you worry less about not having Hart-Simon, but there's still like a big issue, which is that the blow-up argument isn't going to work. Okay, so this is bullet point 2. Okay, and so this is the blow-up argument. So let's say we're in R9. Okay, and in R9, let's suppose that my original surface has a tangent cone, which looks like a cone cross R, let's say, for example, right? And so then I'd like to say that my m prime, which is the perturbation to one side, this is supposed to improve somehow, okay? So now let me do my blow up. I blow up so that this distance becomes 1. But then there's something very upsetting, which happens to you. Let me pretend that I had been prepared and drawn m prime in blue. And so in the blow-up picture, m prime looks somehow like this. I should draw the origin. Or maybe this is bad. So what happened is now I can lie a distance 1 from the origin, but I'm still, it's totally fine for also the blowup of M prime to limit to this. Right? So there's no reason why the blowup of M prime doesn't also give me R across the cone, because before I ruled this out by saying that the cone had no singularities at distance 1. Okay? And okay, you can dream that maybe I chose the wrong blowup scale. And I can't say that I mean, maybe there's a clever argument, but it doesn't seem like you can take a better blowup and avoid this problem. That's, you know, there's possibility that could happen. I'm not sure. Okay. So how do you get out of this picture? So we can't use this blowup argument. Instead, we need kind of a different approach. And what happens is we're going to combine two estimates. So, okay, I'm going to pretend that you know Hart-Simon, just the full smoothness. So I'm going to forget about this. Okay, so the first idea, assuming you know Hart-Simon, is I take my original gamma, and I'm going to find a whole family of gamma, right? So just like I had before, I start with gamma, and I wiggle it up and down in a continuous way, right? And then I construct all the minimizers, in which I label them MS. Okay, of course, they may be non-unique, but I'm just pretending that that's okay. And so let me look at S, which is the union over all S of the singular set of MS. Okay? So it's long gone, but I told you that this set should have Hausdorff dimension at most n minus 7. Okay? But in fact, if you assume Hart-Simon holds, you can rephrase that as saying that the singular set of the whole foliation has the same dimension as you would have expected for a single leaf. Okay? So here, you need to know a little bit about how the proof of the Hausdorff dimension of this looks. But basically, if you have a point here, you zoom in, you look like some sort of cone. And the cone has some spine. And that spine has dimension at most n minus 7, right? So then all the singularities of the actual surface were clustered near the spine. But if Hart and Simon tells you that a surface off of the spine is actually completely smooth. So if you're far enough away from the spine, and you knew Hart-Simon, you'd be completely smooth. So really, this Hart-Simon is telling you about the singular set for the whole family of surfaces. So, okay. So the second fact that you need is that the map, let me take S, mapping from S to R. Okay, so these surfaces MS will be disjoint. So if I have a singular point, then I can tell you which parameter S it was associated to. Right? So this is like X in the singular set of MS. Maps to S. Okay. And then this map, let's say 2.1 holder. Okay. Okay, so here perhaps you're remembering your famous story about the graduate student who was studying 2-holder maps, and they had their thesis turned out to be completely trivial. But actually, that story is kind of silly because there's plenty of interesting 2-holder maps, but they just shouldn't be defined on all of space. Okay? And so let me just tell you 2 facts, or you could think of them as nice analysis exercises. So you have an n minus 7 dimensional set, and as long as this is less than or equal to 2.1, then the Hausdorff dimension of the image is less than or equal to the domain divided by 2.1. Okay? So this, if you know about the Hausdorff dimension, this exercise is like completely trivial. You could just sit down and see what happens, right? So basically, like you cover your set by balls. The image of these balls will have much smaller radius. You just add it up, okay? Right. So you just have to convince yourself that this is the correct, like dividing is the correct way it works, okay? And so this is like a n minus 7. And as long as the Hausdorff dimension of this is less than 1, strictly less than 1, then I've won, because this tells me there's some point not in this image, right? So I'm very happy. Okay, and so I'll leave this as an exercise. Actually, I couldn't solve this exercise, so my colleague Eugenia Melnikova had to solve this for me. But So you should convince yourself also that this this sort of restriction, right? This is equivalent to n plus 1 less than or equal to 10, right? This sort of restriction is going to break down in this method. So I used to have this dream that, well, if you have this two-holder map, right, it should be constant on very large pieces of the singular, like things which are like a manifold, right? A two-holder map on a manifold is constant. But if the singular set were very fractaline, then actually you can construct such a map. So I'll leave it. I can tell if somebody wants to know, I can tell them how to construct this map. But okay. So I'm just about out of time, but let me just very quickly tell you how to get this this holder estimate. And so basically, I'll just more or less draw a quick picture. If you take two minimal surfaces, which are very close to a cone, right? And they're disjoint from each other, right? Then you can control their separation by studying the linearized problem, right? So the separation between m and m prime should be roughly modeled by like a positive okay, so like a positive solution to the linearized equation on the cone. And if the cone is completely smooth, separation of variables like instantly tells you that these two surfaces are splitting, are coming together at a polynomial rate. If the cone is singular, it's a bit more complicated. So actually the distance between the two surfaces may not be improving, but the distance between the regular part is improving, which is what you would expect anyways. And you need to, you should use some work of Leon Simon and Zihan Wang in the singular case. Okay, but I won't discuss that further. It gets a bit technical. So okay, I'll stop here, but I'm glad to take any questions.
Are there any questions?
Yeah. So okay, so you need some replacement for the blow up procedure of Hart-Simon. So either you blow up in a more clever way, that's possible. You mean like there's no reason you need to choose the origin to be the limiting point, and like you could blow up in many ways, but I don't know of one that is better than what we do or what Hart-Simon do. So assuming you can't do that, and you want to play this kind of game, okay, so you want to combine an estimate for the Hausdorff dimension of the singular set of the foliation with an estimate for the Holder norm of a separation estimate. But the problem is that this is sharp, right? Because, well, take a single singular leaf, then you expect, maybe you don't know exact examples of solutions to the plateau problem with this singular set, but I'm pretty sure it should exist. So you expect this to be sharp. And this estimate, well, if you replace 2.1 with a number less than 3, this is also sharp. Well, sorry, so it's possible you could improve this. So yeah, let me just say, in the Simons cone example, so if you take the Simons cone and you take the Bombieri di Giusti, I keep saying di Giorgi Giusti surface, then this surface, the two surfaces come together at a polynomial rate, which is like between, will lead to something between 2 and 3 here. But the one hope is that this surface is not singular, right? So it's possible that, like, so in this estimate, you're really saying that when, like, if you have two singularities close together, then on a pretty big scale, both of them look roughly conical. And then you estimate how close the surfaces are behaving in that conical region. And so that estimate is completely sharp, except this example doesn't have a singularity. So you would need to somehow use in the small scale you have a singularity, and then do something at a much bigger scale. So it's not clear if that estimate could be improved. So I think it's possible that this is a place where one could improve in higher dimensions, but I don't know how to do that. Yeah.
Any other questions? Well, let me ask one. So for the homology problem, are there any additional issues or ideas involved, or
at a technical level, it's a bit annoying because it's kind of hard to do. So Smale bumps the metric to force the minimizer to go to one side, but he only needs to do this sort of like get a minimizer and then limit it back. But we need to get a whole family of like separated minimizers, and that actually becomes kind of awkward. And so in the end, we do it for, we don't get a whole family. You get like a large number. But it's technically annoying to get that to work, but in the end, it's basically, the idea is just what Smale does, but you have to work a bit harder.
Okay, well, if there are no, yeah, one more? That was my first, I first wanted to prove that the space-time singular set is rectifiable. And then you dream that in R9, if you have a rectifiable set and a two-holder function, maybe, I'm not sure if that is enough, or maybe that's like almost enough information to get that it's locally constant. But I guess Aaron is here somewhere, but I tried the Neighbor-Valtorta method for the foliation, and there's some technical problem with proving the rectifiability of the space-time singular set. Actually, I would be interested in if that was possible. When you do we want to compare the like density drop versus the, yeah, exactly. You can't do the change of variables. Yeah. So I couldn't figure it out. So I would be interested to see someone do that, and I guess Aaron would think that was interesting. So yeah, someone should work on that. I'm not sure that it would have extra applications. Maybe because like the downside of trying to use that here is that still it could be 100 dimensional, but rectifiable 100 dimensional, but still fractaling within that space. And so you have this example which I didn't construct for you. Okay, if there are no more questions, let's thank Otis for a beautiful talk.